Welcome to today's webinar, Transformer Protection Fundamentals. My name is Leon Boskov with ABB Power Systems. I'll be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question during the event, please use the question box on the GoToWebinar panel. We will answer as many questions as possible at the end of the event. Please ask your questions during the presentation so it will be available by the end. Today's webinar is being recorded. A link to the recording will be emailed to you following the event. Feel free to forward the link to people you know could benefit from the presentation. Now we'll go over a quick disclaimer. ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to the topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based Protective Relay School, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose. And ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, and profitability. Contact an ABB sales representative for further information. Again, today's webinar is on Transformer Protection Fundamentals and is presented by Jay Hicks. Jay Hicks is a regional technical manager serving the Southeast region for ABB, located in Chattanooga, Tennessee. He's primarily responsible for support in ABB's high voltage line of protective relays and controllers. Prior to his work at ABB, Jay was a senior protection and control engineer at Tennessee Valley Authority. He was responsible for the protection and control design package, consisting of calculations, drawings, interdepartmental interface documents, and construction assisting documents for substations and switchyards. Jay graduated from Tennessee Technological University, with a bachelor's in electrical engineering and is a member of IEEE. So now Jay will start the presentation.
Thank you, Leon. Once again, this is Jay Hicks, and if you have any questions for me, please use the question box. I'll be trying to monitor that pretty consistently, and so feel free to ask any questions that you have and stop me at any time. So the learning objectives for today. We're going to be talking about the transformer construction and fundamentals, three-phase connections and the vector groups. We're going to go over different types of transformer faults, how do they occur and how they look. We're going to go over the protection of the transformers. We're going to stick with microprocessor-based multifunctional relays. We're going to touch a little bit on some of the solid-state relays, however, and see how they used to do it and some of the benefits of going to a microprocessor-based relay on your transformer protection. We're going to look at conventional differential protection. We're going to look at restricted earth fault protection, turn-to-turn fault, overcurrent, inrush, and overexcitation. So what is the transformer? The transformer is one of the most important parts of the power system. The reason for this is it actually interconnects and is your interconnecting link between two voltage systems. The reason you need a transformer in your system, of course, is either to step up or step down the voltage and the current coming out of typically a generating plant. If you just tried to transmit the power coming out of this generating plant, you would see a lot of losses in the transmission system based on your I²R losses. There are many types and sizes of transformers. You have a step-up. Step-up transformers typically in generators. If you want to step up, say, 13.8 kV to 161 kV. You have a step-down transformer. You can see these step-down transformers typically connected to distribution networks. You have auto transformers. Auto transformers are typically Wye-Wye transformers connecting two voltage levels in the transmission system together. Say if you needed to connect a 500 kV loop to a 161 kV loop. You could do this using an auto transformer. Grounding transformers. If you're in the need of a source for zero sequence grounding in the network, you can use a grounding transformer. Other transformers, you could have power reactors, add reactants to the system if needed. You could have a phase angle transformer. A phase angle transformer controls the power flow of the system. Different methods of protection could be fuses. These provide adequate protection for small distribution transformers. Typically, you won't see fuses in large transformers because of just the nature of the fuse. Fuses require a large amount of current to actually blow. And sometimes they allow a large amount of current to actually damage the transformer. You do want to adequately protect your transformer because the repair time is typically long. You don't usually have spare transformers sitting in your switch yard. Both the transformer faults can cause substantial losses because of the damage to the transformer and the need to have a long repair time or have a new one shipped into you. So a basic transformer model is what we're trying to look at here. The gray area is going to be your core of the transformer, and that's the heart of the transformer. It's typically made of iron or some other soft steel. And around this core, you're going to have windings. The P is representing a primary side winding. S represents the low side winding. On these windings, they wrap around the core and induce a flux around the core to induce a voltage and a current on the low side winding if you have power connected to the primary side. To look at this model in the circuits diagram, a model of a transformer, you have your ZP, which represents the resistance and the leakage inductance associated with the transformer. You have this leg here, an IH and an IM. This represents the magnetizing of the core losses associated with the transformer. This is your pay-to-play, per se, that causes this transformer to actually run. These are going to be your losses. And then you have your winding 2, or your low side winding, your leakage and resistance. And once again, this is a current going in. There is a relationship between the current going in and the current leaving this transformer. The relationship's based on the actual turns ratio. So it's an ampere balanced equation where you have the current going in is equal to the current leaving times your turns ratio. Some major aspects of the transformer, the physical aspects. For and foremost, you have the core, and the core is located inside the steel structure of the transformer. The core is surrounded by oil. Oil helps keep the core cool. If you did not have this cooling, the cooler you can keep the core, the more power the transformer can move across the system. Associated with oil, you have an apparatus labeled as number 8. This is going to be your radiators. This is what circulates the oil around the transformer, helps cool the oil. You have an oil reservoir that sits on top of the radiator. Other possible cooling mechanisms could be fans that's connected to this radiator to help cool the oil, to help keep the core at its operating temperature. Numbers 1 and 2, other important aspects are the bushings. This is going to be your connections to the high side of the transformer. Your high side voltage would be 1, and similarly 2 would be your low side bushings, considerably smaller than high side bushings. And of course, this is dictated by what type of voltage you're connected to. Looking inside the tank. Looking inside the tank of the core, we've essentially cut the transformer in half. Inside the core, we're looking at the iron core, and surrounding that iron core, we're going to have windings around that core. The iron core, keep in mind, is at ground potential. The core is at ground potential, and typically this core is laminated, and it's laminated on multiple levels. This lamination helps keep the eddy currents in check. The less eddy currents, the less losses you'll have in the transformer. Closest to the core, you'll have your low side voltage winding. This low side voltage winding is separated by insulation. And you can see that if this insulation breaks down, you'll actually have a phase to ground fault inside the transformer, the core. So insulation breaking down could be a cause of a fault on these low side of these windings, low side of the windings transformer. Also, between these windings, you'll have insulation too. That is a possible cause for faults inside the transformer. This isolation could break down and cause a fault inside the transformer. Showing the model of a three-phase transformer. Considerations of a three-phase transformer. What you're looking at is a three-winding, two-winding, three-phase transformer. Excuse me. NP is representing the windings associated to the high side voltage, and S is the windings associated to the low side voltage. On the leftmost leg will be A phase, B phase, and C phase on the high side. On the low side, you'll have A phase, B phase, and C phase. If you had a tertiary winding, the windings would be connected underneath the low side winding, associated to its individual phases. Also, you need to identify what type of connections your transformer is. Either if it's a Wye-Wye, Wye-Delta, or Delta-wye is an important consideration, and we're going to see that in the next couple of slides. Different winding arrangements that you can have for your transformer. You can have a Wye-Wye, which is a two-winding transformer, a two-winding Wye-Delta, two-winding Delta-wye, a shunt reactor, a three-winding transformer, Wye-Wye-Delta, or you can have an auto transformer. And the big difference between an auto transformer, as kind of shown in this picture, not only is it electrically coupled, but it's mechanically coupled as well from the high side to the low side. Auto transformers typically used in transmission systems, but you can actually manipulate the voltage in respect to the low side voltage by the placement of this low tap changer in this auto transformer. Now this is just to get across the standard ANSI connections of a transformer. This is an unconnected transformer, but with the connections on the outside of the transformer, you'll see H1, H2, and H3, and H0, and that refers to the connections to the high side of the transformer. On the low side of the transformer, you'll have X1, X2, and X3, and X0 if a neutral is used. Now, if this was a three-winding transformer, you have included a tertiary winding, which would be Y1, Y2, and Y3. So H would be high voltage, X low voltage, Y tertiary. Also, your turns ratio needs to be taken into account, and your turns ratio is calculated by the number of turns on the high side over the number of turns on the low side, giving you your turns ratio. So with the standard transformer connections, we can depict this vectorially by if you have a Wye-Wye or Delta-Delta connected transformer, you can see that the connections associated to H1, which is typically A phase, is in phase with the low side connections of X1, or A phase, low side. Similarly, high side H2 will be in phase with X2, and H3 in phase with X3. And this is for a Wye-Wye or a Delta-Delta connected transformer. If you have a Delta-wye or a Wye-Delta connected transformer, there is going to be a 30-degree phase shift. And the phase shift will be that the high side will always lead the low side by 30 degrees, no matter if it's a Delta-wye or a Wye-Delta connected transformer, and we'll see that in the next couple slides. So let's look at the connections of a Wye-Wye connected transformer. For a Wye-Wye connected transformer, you'll have the high side, H1, connected to the polarity point of A phase winding of the transformer. H2 will be connected to the B phase polarity point winding of the transformer, and H3, C phase. Your non-polarity points of the windings will be connected to H0, which will be your neutral connection. Similarly, on the low side, X1 will be connected to the polarity point of A phase, X2, polarity point of B phase, and X3, polarity point of C phase. Since it's a Wye-Wye connected transformer, we know that there will be no phase shift between the currents on the high side in relationship to the currents on the low side. The currents will be equal times a turns ratio associated, shown here as NIA. The same applies if this was a Delta-Delta connected transformer, and if you're in the market of using auto transformers can too be represented as a Wye-Wye connected transformer. For a Wye-Delta connected transformer, these are the connections that it's going to look like. On the high side is Y connected, just like a Wye-Wye, H1 connected to the polarity mark of winding A, H2 connected to the polarity mark of winding B, and H3 connected to the polarity mark of winding C. However, the Delta connected, if you notice, X1 is connected to the polarity mark of winding A and the non-polarity mark of winding C. X2 is connected to the polarity mark of winding B and the non-polarity mark of winding A, and X3 is connected to the polarity mark of winding C and the non-polarity mark of B. This is in turn called an A minus C delta connection. And if you notice, if you do your Kirchhoff's law at X1, you can see the currents leaving the transformer are an A minus C. A coming in, C leaving, A minus C times the turns ratio. If we plot this vectorially, we can see that if we lay A phase currents at 0 degrees, C phase currents at 120 degrees, we take the negative of that, of negative C, and we add these vectors together, we can see a resulting vector of 1 minus A. This gives us a 30 degrees shift, and this now shift is lagging A phase by 30 degrees. When you do this, because of this new magnitude, you affect the turns ratio by a square root of 3. What this does for you is it actually saves the number of physical copper turns inside the transformer. This now gives you a new turns ratio multiplied by the square root of 3. These Wye-Delta transformers typically are seen a lot in your step-up installations. Typically your delta of this Wye-Delta is connected to the generation side, and the Y side, or the high voltage side, is connected to your transmission side. A benefit of this is it isolates any zero sequence currents coming in the generation plant. It isolates the transmission system of these zero sequence currents. For a Delta-wye connected transformer, here we have the Delta connected on the high side of the transformer. If we look at the connections here, instead of an A minus C connected Delta, we have an A minus B connected Delta, with H1 connected to the polarity mark of A and the non-polarity mark of B. H2 connected to the polarity mark of B and the non-polarity mark of C, and H3 connected to the polarity mark of C and the non-polarity mark of B, giving us an A minus B delta. We do our nodal analysis at H1. We can see A minus B. We plot that vectorially, and we can see that there is still a 30 degrees phase shift And now this still the 30-degree phase shift where the high side leads the low side by 30 degrees. Keep in mind that when you do have this delta connection, you will have an affected turns ratio by a square root of 3. Wye-Delta ANSI standard symbols. This is just showing what we've talked about previously about the plotting our phasors vectorially. We can see that no matter what, if you have a Wye-Delta or a Delta-wye connected transformer, the high side will always lead the low side by 30 degrees. And that is, in turn, if you have an A-C or an A-B delta connected transformer. How do we document this phase shift? We do this by the clock system. The clock system documents the phase shift of a particular transformer. The 12 o'clock position is assumed to be the first letter, or the high voltage, and the phase shift is based on the clock position, where each hour of the clock is represented by 30 degrees. So in the first example, we have a YND1 transformer, Y being the Y connection high side of the transformer, and that lays on the 12 o'clock position. The delta, or the low side of the transformer, is at the 1 o'clock position. Here we show the delta at the 1 o'clock position, and we have a separation of 30 degrees, where the high side leads the low side by 30 degrees. Second example, we have a Delta-wye connected transformer, where the high side being a capital D, put on the 12 o'clock position of the clock. The Y connection is at the 1 o'clock position. We have a 30 degrees, where the low side lags the high side by 30 degrees. The third example is a 3-winding transformer with a tertiary. We have a Wye-Wye delta connected transformer, where the Y side, high voltage, is at the 12 o'clock position. The low side is a Y connected transformer at the 12 o'clock position, which there's no phase shift. And then the tertiary is at the 11 o'clock position, where it's shown here by the little d. This gives us that the tertiary now leads the high side and the low side by 30 degrees. So, transformer faults and where the faults occur. For most, we have the winding failures, and this is typically done by the turn-to-turn insulation failures and insulation failures between the windings. Contributing factors could be moisture, deterioration, phase-to-phase ground faults inside the transformer can break down the insulation in the windings, and external faults. External faults, if not cleared quick enough, the transformer sees these external faults, even though the fault is not internal to the transformer. These external faults can easily evolve to internal faults if not cleared quickly. We could have a source of faults could be the tap changer. The tap changer is a mechanical device and electrical device, so there is some coupling there that could fail. You could have short circuit failure of the tap changer, oil leaks, overheating. You could have bushing failures. Bushing failures contributed to aging, contamination, cracking, from earthquakes, shotguns, whatnot. You could have a flashover due to an animal, moisture, low oil. These bushings are oil filled, so if you have a drop in your oil in the bushings, you could have a flashover. Core failures. Core insulation failure, your ground strap burned away, loose clamps, bolts, wedges, etc. Miscellaneous failures, bushings, current transformer failure, particles in the oil, damage in shipment, external faults, core leak welds, overvoltages, and overloads. This is a page from the IEEE guide. Shows what percentage of the causes of transformer failures occurred in the U.S. And at the top of the list, you'll have winding failures. It's 55%. 21% is tap changer failures, 10% bushing failures, and so on. Your power transformer protection. This should trip during short circuit and earth fault, and this should be an instantaneous trip inside of the power transformer bank. It should also be an instantaneous trip in the transformer bay. You should also have protection for external faults as a backup protection if your primary protection did not clear the fault fast enough. The first part is going to be your instantaneous stuff, and the bottom part is going to be the conditions that are time-based. So you should not trip immediately, but trip after if the condition continues on time, such as if you have a continuous overloading condition or overvoltage, reduced system voltage, or overexcitation. And these should be alarmed as well, so action can be taken in the immediate steps, but not necessarily tripping out the bank. How do we detect the internal faults? Well, for faults inside the transformer. So for an internal phase-to-phase fault, we have our transformer differential protection, which is going to be our foremost protection. We have a Buchholz relay protection. Our Buchholz relay, it's a mechanical device that sits inside the transformer. Typically when you have faults inside the transformer, the faults produce heat, and since there's oil surrounding the components, this oil breaks down. When the oil breaks down, bubbles start to form. When these bubbles form, the Buchholz relay can see the flow of bubbles inside the transformer, if you will. When the flow of these bubbles gets too much, the Buchholz relay will actually trip, saying that there's an internal fault inside the transformer. Also, another mechanical device inside the transformer is your overpressure device, or your sudden pressure relay, or SPR. It works on the same basis of oil breaking down, causing gas. This gas expands, causing pressure inside the transformer. Your SPR relay will sense this pressure and trip off the related breakers. As backup protection, you have your distance protection, your overcurrent protection, and your high voltage fuses. And typically, this is backup protection because it needs your distance, your overcurrent, your fuses needs more current to sense the fault. And if that current is present, that could damage the transformer. That's why you don't use it as a primary form of protection. For ground fault, low impedance ground fault protection, you have your restricted ground fault protection, which we're going to go over and do later in the discussion. We have transformer differential protection. We have our Buchholz relay, and we have our backup protection of distance protection, overcurrent, and our fuses. For high impedance ground fault, we have our restricted ground fault protection, sensitive ground fault current protection. We have our residual overvoltage protection and our Buchholz gas alarm. For turn-to-turn faults, these are faults between the winding itself. We have our Buchholz alarm and transformer differential protection. With the introduction of microprocessor relays, we also have a negative sequence differential, which we'll discuss later, that can identify these turn-to-turn faults. High voltage to low voltage winding flashover, we have our transformer protection. We'll see it, so will our Buchholz and our SPR, our sudden pressure relay. So our zones of protection and what area of the transformer we want to protect when we talk about our transformer differential protection. Shown in blue is the zone of protection that we're going to concentrate on, and that's dictated to us by the position of the CTs. And we desire these CTs to be outside the breakers, so the breaker is included in the zone of protection. So the part shaded in blue, we would need instantaneous tripping anytime a fault occurs in that zone. Outside the zone of protection, what's shaded now is where we need restraint. So our differential protection provides us this restraint on these areas shaded in blue, which are outside our zones of protection. The basics of differential protection, which is similar to your bus bar protection, is if we assume load flow from left to right, we can see that the current going in should equal the current leaving the low voltage winding and the tertiary winding. And this current is multiplied. The difference between the transformer and bus is that there is a turns ratio that has to be accounted for. So the ampere balanced equation of the current going in times the turns ratio of the current leaving. Transformer differential protection is quite simple, but there is several aspects you need to take into account for, especially if you're not using microprocessor-based relays. If you're using non-microprocessor-based relays, because of this turns ratio, you need to account for tap settings and phase shift that the transformer poses on the system. So let's look at a differential protection example. Here we're showing a 69 to 13.8 kV transformer, 25 MVA. We notice by the connections that we have a Wye-Delta connected transformer. On the high side is Wye, on the low side is Delta. If we look at our CT ratios, we have a 250 to 5 CT ratio on the high side and a 1200 to 5 CT ratio on the low side. This is because, of course, we have lower amounts of current on the high side and a higher amount of current on the low side. So we have accounted for the current difference on both sides of the transformer by our CT ratios. However, if you look at the connections of the CTs itself, our measuring current transformers, we have a Y-connected CT on the high side and a Y-connected CT on the low side. So if we take, for instance, A phase, the current coming in the CT is proportional to IA divided by the CT ratio. If we look at the current coming in through our CT on A phase on the low side, the current coming in, because of this delta connection, is an A minus C divided by the CT ratio. If this was hooked up, we would see that there would be, the currents would not be balanced from the high and low side. We'll have currents passing through our operate coil, and we would have a misoperation. We look at the numbers from our example. We calculate our primary currents, our MVA, divided by our voltage level times the square root of 3, both on the high and low side. We look at our CT secondary currents. We take our primary currents divided by our CT ratio. We get our tap settings. Then when we add our differential current together, since we did not account for this square root of 3 phase shift on the low side, we can see a 52% or 0.52 per unit excess current in our differential current, which will result in a trip. And just shown vectorially the phase shift from the high and low side. So to do this correctly, and once again, this is before microprocessor-based relays. If we're using solid-state relays, we would have to connect our CTs on our high side in delta. When we do this, we will see by looking at A phase, we now have A minus C current coming into the relay. We have a Y-connected CT on the low side, which reads A minus C, and we can see our currents will be balanced. We do our calculations, look at our CT secondary currents divided by our CT ratios, account for our square root of 3 on the high side, add up our differential current, and because we have counted for that 30 degrees phase shift on the high side, our currents are balanced. We will have no trip. One thing to notice, though, is the tap settings. Your tap settings on your high side have changed, not only by your 30 degrees phase shift, but you have a square root of 3 now because of that delta connected in your CT, which affects your tap settings. So tap settings need to be accounted for, and your phase shift. So, Transformer Differential Protection 101. Transformers with Delta and Wye connections. You must account for the magnitude square root of 3 compensation, as shown in our previous slides. What also you need to account for is that the zero sequence currents for any external faults must be blocked. Your solution for conventional differential protection is to connect the CTs on the Y side, connect those in Delta, and connect your CTs on your Delta side in Y. If you have a microprocessor-based relay, you can do this via settings inside the relay. If you have a Delta-wye or a Wye-Delta connected transformer and you're using a microprocessor-based relay, you can connect all your CTs in Y. Once you've done that, there is a setting typically, and different vendors do this differently, of how to filter your zero sequence currents from your differential. So your differential protection is affected by the tap settings. So typically the best way to do it is to only use relays that require nameplate information from the transformer. And the nameplate information includes your number of windings, your voltage level, your CT ratios, your MVA, and your vector group. With this information, you can input this nameplate information into the microprocessor-based relay. It will then in turn calculate your turn balance equation. So you can set your CT ratios at any level you want to. The turn balance equation is calculated for you. Now we need to look at what causes a false differential current. Different sources of false differential current could be from zero sequence, from transformer inrush, from CT saturation, or from overvoltage or overexcitation. And these are the 4 things we're going to look at and how to account for them in our differential protection. So to block zero sequence current from the differential circuit, we can do this by utilizing the Delta connected CT on the Y side of the transformer. So in this example, let's concentrate on the CTs closest to the transformer. The CTs are both connected into Y. We can see that the Delta side of this transformer has no source of zero sequence currents, so the relay will see zero sequence currents. However, on the Y side, since we do have a ground connection and we have a Y connected CT, we have a source of zero sequence currents, and the relay will detect these zero sequence currents, causing the relay to misoperate. If we connected the CTs into Delta on the Y side, we can see that there will be no zero sequence currents circulating going to the relay. So your net zero sequence currents will stay zero, hence not tripping. Once again, this is using solid state relays. If you were using a microprocessor-based relay, you can use a Y connected CT on the Y side. Use your settings inside the relay to filter out your zero sequence currents. Another form of false differential current is inrush current. So we'll go back to our picture of the transformer model and how to represent this inrush current. If we look at our circuits model, I mentioned that IH and IM represents the magnetizing leg, or the current flow of the primary side, which will not produce any current on the low side. So for example, we connect this circuits model, EP, to a source. We open up ES and connect it to no load. We will still have currents circulating through this portion of the transformer. This accounts for the losses of the transformer, and what losses that you don't, the currents you don't see coming out the low side of the transformer. So influencing factors on how much inrush current you'll have. Typically, For the smaller transformers, you'll have a higher peak inrush current, but it will typically generate for a shorter amount of time. The larger the transformer is, you'll have a smaller amount of inrush. However, that inrush time is a lot longer. Also considering factors is when you switch the transformer on from the system and start bringing it online, when you start saturating the transformer. When you bring the transformer online at the voltage of 0 crossing, that's when you're going to experience your peak inrush. If you have current going into the transformer, no current leaving the transformer, the differential sees that as a fault condition and trips. So we need to have a way to account for this inrush condition. What also influences the inrush current? What side you actually energize the transformer on. Since the low voltage winding is closest to the core, if you energize the low voltage winding first, you can typically expect inrush currents of 10 to 20 times greater than the rated current. However, if you energize the transformer on the high voltage side, typical inrush currents are 5 to 10 times that of the rated current. Remanence. The higher the remanence, or the higher the flux inside the core, is contributing factor, the higher the inrush is. Also, the impedance of the system is a contributing factor. Energizing from a lower source impedance results in a higher inrush. Plus, you'll see the highest inrush generally at generating plants. So on this BH curve, trying to represent the inrush and the remanence inside the core, we have the inrush is directly proportional to the voltage applied to the transformer. And here we can see on this BH curve the inrush current going through the flux of the core and its rotation. We can also see the total flux, and this of course is the worst case if we have a closing of the breaker feeding the transformer at the 0 crossing of the voltage. You can see the total flux will be at its peak after the half cycle of voltage. This would be the worst case scenario, and this is what you need to account for to block your differential protection from operating. So how do we detect inrush current? Well, with the relationship to this total flux, the current seen going into the transformer will not have the 60 hertz characteristic. It will have a 120 hertz characteristic footprint. And that's what I'm trying to show on this graph, that the footprint of the current going into the transformer is going to be at a second harmonic characteristic. So if there is a way to monitor that second harmonic characteristic, you would know you're in an inrush condition. And that's how the microprocessor relays see this inrush condition, is looking at the current flow at the second harmonics. So most protection schemes look at the second harmonics to distinguish between inrush current and short circuit current. The reason for this is the short circuit current has only a very small second harmonic component. However, the inrush current has a very significant second harmonic component. The minimum percent ratio, second over fundamental, occurs when the transformer is energized at angle 0. And we've seen that in the previous slide. This results in our peak inrush current that we need to account for. And protection engineers should set relays based on data from the transformer manufacturer. So if we're looking at second harmonics, we can see that the percent second harmonics during a magnetic inrush is around 63%. However, for any internal faults or CT saturation, these components are very small compared to our magnetic inrush component. We also see that there is actually a high or a large fifth harmonic component to this current. With that in mind, you can use the combination of both the second and fifth harmonic to identify your inrush condition and restrain from tripping. Other blocking options that you can have is a total harmonic condition, meaning that all three phases show the characteristics of second harmonics. Another blocking option is cross-blocking. What that means is if one phase detects this second harmonics, it will block all three phases from tripping the differential. Another source of false differential current is when you go into overvoltage or an overexcitation condition. And what this happens is if you're pushing too much current through the transformer, the core can only output so much, and once you reach that point, you still have a greater current going into the transformer. However, that is not directly proportional to how much current is leaving the transformer. One way to identify this is using third or fifth harmonics. The current going in will represent, when you're in an overvoltage or an overexcitation condition, both third and fifth harmonics. However, you do not want to use third harmonics ever. The reason for this is because third harmonics are prevalent across the system, so it's safe to assume that fifth harmonics will represent the condition of being in the overvoltage or overexcitation condition. So if you see a second or fifth harmonics, plan on blocking your differential. Overexcitation exists if the per unit volts over hertz exceeds the design limit of the transformer. The voltage exceeds 105% at full load or 110% no load at rated frequency, or if it goes below 95% full load, 90% no load at a rated voltage. Look at the manufacturer's time curve to determine if you need to block or trip during this overvoltage condition. There's two ways to actually detect overexcitation. You can use an input from the VT, the metering VT on the high side of the transformer. If you do not have a VT connection, you can calculate it using fifth harmonic current restraint measured from the relay. There is a note that says apply blocking or tripping with caution, because if you're in an overvoltage or overexcitation condition, typically you're in the hottest of days, coldest of nights, and you're having a strong load on your low side. So if you trip, you're going to put a lot of people out in the dark. If you block and you don't trip, you could possibly overload the transformer. When you're setting up your differential, you'll have this picture showing two regions, a flat region and a slope region. We have current in this graph is representing current in the restraint coil, represented by the x-axis, and the y-axis we're representing the differential current seen by the relay. In ideal circumstances, we would of course want to set this at 0, but of course we don't have ideal circumstances where our pickups cannot be set at 0. Anything other than 0 would trip the transformer. We have to account for certain errors. That's what raises our minimum operation current. Sources of errors are the low tap changer range, especially if you're not monitoring the position of the low tap changer. The differences in your high voltage and low voltage CT errors. For Class C, this is 10%. So on the high side, 10% plus the low side, 10% will give you 20% error. Excitation current. That offers a 2% error that we need to account for, plus a fudge factor, a margin of error of 5 to 10%. So setting up our slope, we have a CT error of plus minus 10%, a low tap changer variation of 10%, Overexcitation current at rated voltage around 1.4%, and our margin of error at 5%. We add these up. These different errors gives us a minimum pickup setting of around 0.37 per unit. With these errors in mind, we can calculate our slope setting. Slope setting set after 1 per unit. We will see that we'll have about a 35% slope. And with this 35% slope, with this error, we take into account the higher current in the restraint coil will give us more of an error in our differential protection. So our errors are accounted for, shown here on the right. Most microprocessor relays have 3, 4, 5 regions that you can set. Here showing 3 regions, M2 being a slight slope, and M3 having a greater slope, giving you more security through your either CT saturation or errors in your calculations. That's why you would see a higher slope here at M3, typically for CT saturation. So, I mentioned before, if the low tap changer position is monitored, you can actually increase your sensitivity of your pickup setting. So if you can monitor it, your low tap changer, and what position it's at, you can set your current and slope setting at about 0.15 to 25 per unit. Restricted earth fault protection. And here is an example of a protection scheme that typically was not done in the solid state realm. This has been introduced in the introduction of the microprocessor-based relays. And what restricted earth fault does is you're wanting to protect faults that are close to the neutral leg of the transformer. So, for instance, if you have a fault on the neutral, say at this point right here, I hope you can see my mouse, you're going to have no voltage drop. So it'll be very difficult to see any change in your zero sequence current. However, when you get up the winding, when the fault evolves up one of the windings, there is going to be a flow of zero sequence current coming from this transformer, from this neutral point out the transformer. The way that restricted earth fault protection works is you have your connections on the high side of the transformer. You have a connection on the neutral leg of the transformer. You sense, or you do a differential of your zero sequence current, either coming into the relay or coming into the transformer or leaving the transformer. If you have a phase to ground fault outside this transformer, say a grounding point here, you would have zero sequence currents leaving the transformer, the neutral leg, going through the transformer and out to the system. This relay will measure the zero sequence currents coming out of the transformer, and it will calculate the zero sequence currents leaving the transformer. It will perform a differential, and it will see a net zero sequence current inside the transformer and restrain from tripping. However, if you have a fault inside the transformer, it's very close to the neutral, you will see zero sequence currents coming from the transmission side, plus you'll see a zero sequence currents coming through the neutral of the transformer, showing us a net zero sequence current that the relay sees and operates. Turn-to-turn fault detection. And what turn-to-turn faults are is when you have two windings in the same phase actually touch, and I'm trying to represent this by this NT. What happens is if this was a 20 to 1 winding transformer, these two windings touch, and instead of 20 to 1 winding transformer, you have a 19 to 1. All the flux and current that was shared between these two windings now is going through one winding, one new winding. What happens when this occurs is, unfortunately, the differential does not see this change in current because the transformer forces the currents to be balanced. However, our turns ratios has now changed, giving us essentially a hot spot inside the transformer. The sudden pressure relay will eventually see this condition. However, if it does, it's typically too late and it has a tendency to misoperate. So our solution for turn-to-turn fault detection is what we call a negative sequence differential. Let's see if we have any questions so far. I don't see any questions, so we'll move on. So turn-to-turn fault detection. The way this works is, let's move down to these examples, these pictures at the bottom. If we have a fault outside the transformer, the zero sequence currents leaving this fault will go through the transformer, through this CT, out this CT, giving us essentially a balanced differential associated to negative sequence currents. However, when we have a fault inside the transformer itself now becomes a source of negative sequence currents. The currents would leave the transformer. The relay itself would see a net negative sequence currents and trip, indicating that you have a winding failure inside the transformer. Overcurrent protection and coordination. The importance of this is, as a backup protection, is that this is not protecting for faults inside the transformer, as well as it's protecting for faults external to the transformer that the transformer does see. Because every time there is a close-in fault or faults close to the transformer is affected both through the thermal effect and the cooling effect. Mechanical parts start to break down, and that needs to be considered when setting your overcurrent protection relays. The transformer comes with a capability curve, and if you exceed that transformer capability curve, you can guarantee to have damage to the transformer. So here we're trying to show the coordination between your time overcurrent, your instantaneous relays, with relation to that transformer capability curve. For time overcurrent protection, inverse time characteristic relay provides the best coordination, especially for other relays downstream. Settings of 200 to 300% of the transformer self-cool ratings are typically used. Fast operation is not possible, and that is because these time overcurrent relays need to be coordinated with other relays downstream. Instantaneous protection needs to be fast operation on heavy internal faults. These are typically your overcurrent protection. Settings at 125% of the maximum through fault, and that's typically monitored on the 125% of the maximum through fault, and the worst case scenario would be a low side three-phase fault. And of course, you need to consider the inrush current, and the settings should be above that for prevent misoperations. So, to review what we've been over, for a typical protection scheme for power transformers, we have our transformer differential protection, which is our #1 protection. We have our negative sequence turn-to-turn differential fault protection. We have our restricted earth fault protection for faults close into the neutral of the transformer. We have our sudden pressure relay, our Buchholz relay. We have our overcurrent protection on the high side, our ground overcurrent protection is backup. We've talked about thermal overload protection and our overexcitation protection. With that, I'm done. I do appreciate you listening in.
Jay?
Take time. I'll turn it over to Leon now.
Jay, can you hear me?
Yep.
There are actually a few questions. If you could answer those, do you see them?
Um,
There should be 8 of them.
I can't see them.
Okay. I guess I'll just read them to you individually then, if you could go through them and answer those.
Okay. I'm sorry about that, guys.
Yeah, that's strange. I don't know why that's happening. Okay, the first one is asking what type of oil is usually used. I'm assuming in a transformer nowadays.
It's going to be the same oil that's used in the older transformers. I don't know the chemical composition of it, but it's the highly toxic oil that causes an EPA nightmare anytime it leaks. I don't know the exact composition. I just know it's pretty nasty stuff.
Okay. Second one, are primary and secondary windings on top of each other?
Yes, they are. They are on top of each other, and that's shown in this cutaway. And this is for our major transmission system transformers. And yes, they are on top of each other. This is actually a real life cut view of what the transformer windings are located and look like.
All right. Next is this ANSI system to document vector group?
Well, the clock system documents the vector group, or the phase shift.
Okay. We'll move to
the question is.
What is the significance of having phase shifting between high voltage and low voltage winding?
The benefits are you're able to isolate zero sequence contributions from one side to another if you're using a Y or a Delta connected. The other added bonus is if you have a Y-Delta connected transformer is that you don't have to use as much copper to create that turns ratio that's desired.
Okay. Next one. What overvoltage level in percentage would be a dangerous level at which the transformer should be tripped, and why?
Dangerous overvoltage levels will need to be looked at the transformer comes with documentation that shows you. Let me see if we go back to this slide. It'll show you the capabilities of the transformer, both self-cooled and non-cooled. And if you have sufficient cooling on your transformer, your voltage can actually rise. You have different set points that the transformer manufacturer will provide to you of what your limits are, and that is in the documentation of the transformer. So it's difference between, so you have different factors you have to account for. If you have external cooling, how good your oil, how old the transformer is. This is all documented on these variables are considered when you set your overvoltage relays, which is documented in the manual of the transformer provided to you.
Okay. Next one wants to discuss the location of the low side three-phase faults.
What was that again?
Well, it's asking to go back a slide. I'm not sure which slide it's referring to, but it wants to discuss the location of the low side three-phase faults. And I think that was towards the end. It's the second to last slide.
I'm not sure. I'm not sure of the question. Location of the three-phase faults. Okay. the worst case is a close in, so just outside the transformer bay is your worst case. That's where you need to do your study at.
Okay.
The worst case is just external to the relay. A close-in, external, low-side three-phase fault will be your worst case.
Okay. The next one is, why is negative sequence used for turn-to-turn faults?
Because there's no, let's see. The reason negative sequence is used for turn-to-turn faults is there is no other way to see these turn-to-turn faults, since you cannot rely on your differential and your sudden pressure relay, because there is an imbalance in the turns ratio. So you're instead of having symmetrical, you have an asymmetrical component across those turns that will, once calculated those resulting vectors, you will see a negative sequence component to it. That is the solution, because previously we didn't have, could not rely on the SPRs and the differential for picking up those kind of faults.
Okay, next question is, what is a typical setting for negative sequence turn-to-turn fault protection?
I've seen it set to 10% per unit. That's the typical setting our relays use. So if you see anything greater than 10% per unit of your rated current, and that's based on that differential. So any excess differential current over 10% per unit.
Okay, the next one is asking, it's saying that most of the auto transformers are Wye-to-Wye connected. Could you please elaborate on that?
They're not Wye-Wye connected, but they can be represented as Wye-Wye connected. So when you're understanding them and you're doing your circuit analysis on a auto transformer, it can be represented as a Wye-Wye connected transformer.
Okay. I don't know, I'm not sure what trafo stands for, but it's asking, having Wye-to-Wye trafo, I'm assuming transformer, with zero phase shift could make the transformer protection simpler?
Say it again.
It's saying having Wye-to-Wye transformer with zero phase shift could make the transformer protection simpler?
That is 100% agreed.
Okay.
That is 100% agreed. However, you're going to, especially if you have a Wye-Wye connected transformer into a generating plant, if you're then giving a source of zero sequence current to that generating plant. And most faults inside a generating plant are phase to ground, which can cause excess damage to the generator. So, yes, it makes our jobs easier to set the relays. However, we got to look at safety of others. So that's why.
Does the 12 o'clock position always refer to the high voltage side of the transformer?
Yes.
Okay. What is the general standard slope setting for differential relays? Is it 25% and why?
Well, it's based on your error calculation. So you got to look at your CT errors, if you're using a low tap changer, if it's actually being monitored, and whatever fear factor you put into it, and that based on your calculations of your errors, that's going to dictate what type of slope you're going to be using.
Okay.
And slope also.
This question actually goes back to one that you previously answered. It's asking, why is an external secondary face-to-face fault the worst case scenario?
Because that's going to, on the low side, say the question again. Why is there
external secondary face-to-face fault the worst case scenario?
because that's you're going to see your most current going through a face-to-face, a three-phase. Though the worst kind of fault is a three-phase fault, and that's where you're going to see the most damage because of the most current flow inside of a three-phase fault.
And this is the last one that I see. It's asking, in industry, which type of transformer winding configuration is the preferred type generally for transformer protection?
You're breaking up. Say it again.
It's asking, in industry, which type of transformer winding configuration is the preferred type generally for transformer protection?
The preferred winding?
The preferred winding, yeah, for transformer protection.
They're all preferred windings. I don't understand the question.
Okay. We'll move on to the next one then. What is the trip time of differential relays and cycles?
It's going to be sub-cycle. I mean, that's going to be vendor specific. However, you're looking at less than a cycle.
Okay. Yeah, it looks like that's pretty much it. Thank you very much for answering those.
Okay.
And thank you for joining, everybody. This concludes the seminar.